So chapter 13 is on gravitation, okay? And really we'll be talking about Newton's law of gravity. Okay, so we'll cover some of these four concepts. We'll talk about Newton's law of gravity. Um, we'll talk about gravity near, inside, and on the surface of Earth. We'll talk about gravitational potential energy. When can you associate a potential energy with a force? When it's a conservative force. Okay, so that's when you can associate a potential energy. What that means is, if you remember, the force can be written as the gradient of the potential energy. Okay, so that's when you can, okay, but anyway, we won't worry about that. We'll talk about Kepler's laws of planetary motion. Okay, so Kepler came up with his laws describing how the planets go around the sun, and Kepler came up with these laws before we knew about Newton's law of gravity. Okay, so Kepler didn't know why the planets go around the sun. Newton was the one who explained it. Okay, so we'll look at satellite motion. And nowadays there's so many satellites up there. Your lives depend on it. This thing wouldn't work without those satellites. Again. Mr. Newton explained tidal forces. Okay, he explained how tides occur. Okay. So the thing with tides is the following. Yeah. So here's the moon, here's the earth. The earth has an ocean. Okay, and what happens is, this is just an exaggerated view. Okay, these oceans bulged like so. Okay, so the moon is attracting this portion of the ocean, and it bulges like that. That is sort of intuitively easy to understand, but there's a bulge, equal bulge on this side. Okay. And Mr. Newton was the one to first explain these tides, okay? And we'll talk about that. So, in Einstein and gravitation, we'll talk about the improvement on Newton's theory, okay? Okay, so Newton gave us the theory of gravity in, let's say, 1700. Einstein gave us his theory 250 years later. So this was an improvement on that. That's 250 years later. Okay. And we waited another 100 years and we don't have the final theory yet. So the final theory will be a quantum theory of gravity. So for instance, we can't. So we need a quantum theory of gravity to be able to say what happens inside a black hole. We don't have that yet. So we don't. What Einstein says is wrong about what happens inside a black hole. It's not the final word. All right. So this is what we're going to talk about. We're not even going to talk about this. Even this is most grad schools don't even teach this, well, okay, unless they have a program in specializing in that. So this is what we'll talk about. The specialty. So what this slide tells you is, if you want to talk about things that are moving fast meaning speeds comparable to the speed of light, then what you need is the special theory of relativity. Okay. So everything we've studied so far is slow-moving objects and so on. So special theory of relativity is a limit of general relativity with zero gravitational fields. Okay. So general relativity is able to handle strong gravitational fields and fast-moving objects. So, and Newton's theory of gravity is a approximation of this general relativity in weak fields and slow moving objects. Okay, so that's what we're going to talk about. All right, so what Mr. Newton told us was that every object in the universe attracts every other object. Okay, so every object attracts every other object. And what he gave us was a formula for the magnitude of this force. Okay, so this guy attracts him with a force, and this guy attracts him with an equal and opposite force. Okay, so all we need is a formula for the magnitude of this force. And there's the magnitude of this force. So the magnitude of the force is given by the product of the masses divided by the distance squared. And this constant of proportionality is the same for all objects. It could be 2 bacteria, it could be 2 planets, it could be 2 stars, it could be 2 galaxies, it could be 2 people, it could be 2 dogs. This constant is the same. So that's why it's called a universal gravitational constant. Yeah. And it turns out that this gravitational constant is very weak, very small. And that's why the force of gravity is very weak. Okay. So if you want this force to be noticeable, the masses, one of the masses, at least one of the masses had better be large. Okay. So for instance, the gravitational force between 2 people sitting next to each other is equal to roughly the weight of one of your hair. That's why you don't fall toward each other. Okay. But if one of the masses is Earth, then you can get on the table and jump off the table and you'll fall toward the Earth. Yep. So this constant is very small. In fact, apparently this is still one of the least accurately measured physical constants. Okay. So Newton came up with this theory in 1687, and this constant was not measured for 100 years, almost 100 years later. Okay. So it's the weakest of the 4 forces because the gravitational constant is very small. Okay, so the force of gravity attraction between these 2 objects is 10 to the minus 7 newtons. The force with which Earth pulls on you is 10 to the 3 newtons roughly. So the force with which Earth pulls him is 10 to the 3 newtons. The force between these 2 is 1 billion times weaker. It's 10 billion times weaker, but so that's why he doesn't fall toward the dog. Okay. What interacts gravitationally? Everything. Okay. All masses interact gravitationally. So you are attracted to every object in the universe gravitationally. Okay. So galaxies also are attracted towards each other, and also, if let's say this is just an imaginary experiment, you can take 2 galaxies, set them apart and at rest, so eventually they'll move towards each other and they'll collide. Okay. Everything in the universe is moving. So that's a powerful statement. Nothing can be at rest. Yeah. Everything in the universe is moving. All right, so these 2 galaxies are on a collision course, the Andromeda and the Milky Way, and will collide in another 4 billion years. Okay. So here's in 1800, remember Newton came up with this law of gravity in 1687. So about 115 years later, G was measured. And this is called weighing the Earth, because once G was measured, that's when we knew the weight of the Earth. We didn't know the weight of the Earth. We had no idea about the weight of the Earth till 1800. Okay. And in fact, the day that was measured, we knew the weight of the Earth, we knew the weight of the sun, and so on. Okay. So that's why we call this experiment weighing the Earth. And here's how it was done. Okay. So it's a very sensitive experiment. So here's a metal cable. Okay. And you have a metal cable like this. If you twist it, what it wants to do is it wants to twist back. So let's say this is a metal cable you put, and so this is called a torsional pendulum. So now we'll do the following. Here's the metal cable, and we got this thing suspended, and if we twist this, the cable will twist back. It'll oscillate like that, actually. Okay. So what we'll do is, so in this cable, okay, so there is this cable, and we have two spears at the end. Okay. And then what we do is we take these two large masses. Initially they're at the bottom, and so here's the untwisted position of the two masses. And what we'll do is, so these masses were at the bottom here, and then we'll raise them and bring them next to these two little spears. Okay. What does this massive guy do? He attracts him, and so this guy moves closer to him. This guy moves closer to him. The angle through which they twist will depend on the force of attraction. Okay. And also, we measured previously how much torque is needed to twist this cable, that you can measure independently. Okay. So you can calculate the force that this is exerting, the torque that is needed to turn the cable through that angle. Okay. So the torque needed to twist the cable through that angle. Okay. And in this case, the torque is this force. So the torque is this force times this length, twice that. Gmm by r squared, 2 times the length is minus kappa theta. Okay, so you measure this angle theta, the angle through which it turned. We know this, we know this, we know this, we know the masses, we know the distance between them, and you can calculate G. Okay. So that's how G was measured. Okay. Now here's the thing. What is the acceleration due to gravity on the surface of the Earth? 9.8 meters per second squared. Okay, so mg equal to g mass of the Earth times the mass, this mass, divided by the radius squared, radius of the Earth squared. We've known the radius of the Earth for a couple of thousand years. Okay, some Egyptian dude measured it. So we've known this for 2,000 years. We know this mass. We've measured this. This we know. Now suddenly Mr. Cavendish measured this in 1800. Now you can know the mass of the Earth. Okay. So soon as you measured G, the whole can of worms opened up. Okay. So a whole new world opened up to us. Okay. Now here's the first question. Okay. So you know the radius of the Earth. Now you calculated the mass of the Earth. You can calculate the average density of the Earth. The density is the mass of the Earth times the volume of the Earth, 4 pi by 3 RE cubed. Okay. The afternoon that you measured G, you could calculate the average density of the Earth. There's the average density of the Earth that came out. You walk outside, pick up a handful of dirt. What you find is the density of the dirt is 2.5 grams per cc. So what does that tell you? That's right. So the density, so that's the afternoon we knew that the Earth was not uniformly dense. Okay? So here's the density profile now. Okay, so there's the density, okay, on the surface of the Earth, about 2.5 grams per centimeter square cubed. And then the density of the mantle, density of the outer core, and the density of the inner core, which is about 15 grams per cc. All right, so now we know this detailed density map. Okay, now this is actually only about maybe 30, 40 years old, maybe 50 years old. Okay, this wasn't, so to get this picture, uh, here's how we got this picture. Okay, so this thing is possible only with a lot of computational power. Okay, so to understand this, okay, you need to understand the following. So here's a wave traveling in a medium. Wave will travel in a medium, okay, and now let's say it hits another medium. If it hits another medium, if the medium, if the velocity is, okay, if the velocity in this other medium changes, then the wave will bend, and this is called refraction. Okay, so for instance, if a wave is traveling like this, and if in this, if this is medium 1, medium 2, if in this medium it gets slower, then the wave will bend this way. If in this medium it's getting faster, then it'll bend that way. Okay? And the speed of a wave in this medium depends on the properties of the medium. Density of the medium and so on, if it's a mechanical wave. All right. So here's this deal. Here's an earthquake. Earthquake are mechanical waves, sound waves, so to speak. Okay, we call them seismic waves. Okay? And here there are seismometers all around the world. Okay, so this earthquake happened, and after a certain time we detected the wave here, 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 and all that. So you can reconstruct how the wave traveled. So the wave must have traveled this way, and you can reconstruct the velocity profile and then the corresponding property of the material. So you need earthquake data from millions of earthquakes and lots of seismometer data to reconstruct all of that. And from that, you can reconstruct this. So it needs a little bit of computing power. Okay. So that's how we know the inner structure of the Earth. Because, the radius of the Earth is 4,000 miles, and the deepest hole we've dug is about 4 miles. We barely scratched the surface. All right, so what this says is gravity outside an object. So if the object is uniform, if the density is uniform actually, so if it's all it needs to be is radially uniform. But anyway, if the density is uniform, if you're outside the object, okay, the gravitational force on you is independent of the size of the object. Okay, so what that means is if you have a satellite, this is the space station going around the Earth, the centripetal force is provided by the gravitational force of the Earth. Okay, the orbit of this guy would not change if you turn this into a black hole. If our sun became a black hole, okay, our orbit would not change. Of course, we wouldn't have sunlight, but that's a different story. Okay. So what we're saying is, if for a symmetrical object, the gravitational force will be unaffected if this turns into a point object. So the gravitational force exerted by a finite size spherically symmetric mass distribution on a particle outside the distribution is the same as if the entire mass were concentrated at its geometric center. Okay? So if you turn this into a point mass, the force would still be the same. Okay, here's the superposition principle. Okay. So if you have several objects, like in the solar system, okay, the force on this guy, how do you calculate the force on this guy? Well, calculate the force between these two guys, calculate the force between these two guys. The force between these two guys is not influenced by the presence of that guy. Okay, so you independently calculate the forces and then just add up the vectors. All right, so now if you're playing around with planets and all, this is fine. But this would not be true if you were playing around with black holes close by black holes. Okay, but not too many people get to play with that. So, and then you would use the better theory, Einstein's general theory of relativity. Okay, so that's the superposition principle. Okay, what is the radius of the Earth? I'm sorry? 6,400 kilometers, about 4,000 miles. Okay. All right, what's G on the surface of the Earth? 9.8 meters per second square. Okay. So let's say, what is G about 100 miles above the surface of the Earth? About 9.8. Okay. So, but if you go far, far away, comparable to the radius of the Earth, now G changes. Okay. G decreases as you go further and further away. Okay. For it to be noticeable, you have to go a distance comparable to the surface of the Earth. So for instance, if you go 4,000 miles away, okay, so here's the equation. mg is mg equal to gmm by r squared. So G is given by this formula. G is G, mass of the Earth, divided by the distance from the center of the Earth. So if you're on the surface of the Earth, this is 9.8, and this is the radius of the Earth. If you're 4,000 miles above the surface of the Earth, that is, you're twice the radius, then that would be 2r squared, so that would be 2.5 meters per second squared. So 4,000 miles above the surface of the Earth, G has fallen to 2.5 meters per second squared. Okay. So G depends on the distance from the center of the Earth. Okay. So there is the radius of the Earth plus the height above the surface of the Earth. When this is 0, that is equal to 9.8 meters per second squared. Okay. So here is G naught, that's this gravitational acceleration on the surface of the Earth, and this is the height above the surface of the Earth. Okay, so here's G given in terms of that. When h is 0, this would be G naught. On the surface of the Earth, that's 9.8 meters per second squared. And here is the calculation for various heights. So the radius of the Earth is, the radius of the Earth is about 6,400 kilometers. So if you're about 6,000 kilometers above, see, G has reduced to 2.5 meters per second squared. Okay. So here's a map of that. Okay, what this tells you is, see, this arrow tells you G is always pointing towards the center of the Earth. Okay, so if you were to fall from here, you're always falling towards the center of the Earth. Okay, and what these arrows tell you is the magnitude of this arrow tells you the value of G at that location. So the magnitude of this arrow on the surface is 9.8 meters per second squared. And you see, as you're further up away, the magnitude of the arrow is smaller. Okay. So if you were 4,000 miles away, then the magnitude of the arrow would be 2.5 meters per second squared. On the surface of the Earth, it's 9.8 meters per second squared. Okay, so this is the gravitational field. And as you can see, it's a vector field. Okay. Okay. Now we'll try and understand what the word apparent weight means. Okay. So let's say you're standing on the ground. What happens? The Earth is pulling you down. You actually don't feel the force of gravity. So what is it that you feel? The ground is pushing you up, preventing you from going through the ground. Okay. And that is your apparent weight. So this force is your apparent weight. So for instance, let's do the following experiment. Here's an elevator. You're standing on a scale in the elevator. Gravity is pulling you down, and the elevator is pushing you up. Okay? The scale is pushing you up, and that's your apparent weight. And if the elevator is not moving, this will equal mg. Okay? Now let's do the following. Let's cut the cable. When it's in free fall, this thing is accelerating g. You are also accelerating at g. This goes to 0. Your apparent weight goes to 0. So you're weightless. Now, but that's a dangerous experiment. So here's a simpler experiment, not as dangerous. So do this underwater. Mg, we'll learn about buoyant forces. And so now the force with which the scale is pushing you up is 0. Your apparent weight is 0. Okay, so you're weightless underwater. All right, so now let's come back to this. So your apparent weight is the force with which the ground pushes you up. Okay. So here's the Earth, here's this object, there's the force of gravity that pulls it down, and there's the apparent weight. Okay, so that is true. That is true. So this will equal mg. But now let's do the following. Now let's make the Earth spin. So when the Earth is spinning, what you need is, so you're going in a circular path, uniform circular motion. So v is your speed. Then what is it that you need? You need a centripetal force. Where is the centripetal force coming from? There's only two forces acting on you, the force of gravity and this normal force. You need a centripetal force in this direction. So the centripetal force is the force of gravity minus the normal force. So as soon as you start the Earth spinning, now, well, this guy doesn't become any smaller. This has to reduce. So as soon as you start this world spinning, your apparent weight has decreased. So I'll tell you a very neat thing about that. So you see, there's the force of gravity. Force of gravity minus the normal force is providing you the centripetal force. Okay. This guy doesn't change. So because of this velocity, this decreased. So let's look at the equation and let's look at this equation. Okay, let's make you go faster and faster. This has to become smaller and smaller. make this fast enough where this has to go to 0. Okay? So you could stand on a scale and it would be reading 0. So you want to lose weight, all you have to do is make the Earth spin faster. So here is a beautiful thought. Do you guys know, well, how fast does the Earth rotate? Yeah, once in every 24 hours. So by the way, so the radius is 4,000 miles. 2 pi r, 2 pi is 6. That's 24,000 miles once every. So if you're at the equator, you're going at about 1,000 miles an hour. Okay? That's your speed. All right. Do you guys know how long it takes for the space station to go around the Earth? It's 90 minutes. You're weightless in the space station. So if you make the Earth spin instead of once in 24 hours, if you make it spin once in 90 minutes, this will be 0. Your apparent weight at the equator would be 0.
Get right on that.
What's that?
I'll get right on that.
Yeah. In fact, if you wanted to go to space, all you have to do is go walk off into space. It would be as easy as that. So that would be at the equator. At the North Pole, Santa Claus would still be weighing the same. He can't lose his weight. All right, so apparent weight is that. Okay. Now here's another interesting fact. All right, so just a few more slides. Okay. When you're building a building, how do you make sure that it's straight up? How do you make sure that the building is straight up like this and not crooked? Yes, so you use a level. Okay, what you do is you suspend a weight, heavy weight, in a plumb bob. That's what it's called. The word was escaping me, and you build it parallel to the plumb bob. Okay? All right. Now let's look at this guy. Okay. So let's say you're building something in New York. Well, the Earth is spinning about this axis. New York is going in a circular orbit like that. Okay. So by the way, I'm not going to go through the calculation here. If you're at the equator, remember you're going at 1,000 miles an hour. If you're in New York, the circle is smaller. It's still taking you 24 hours. So you're going at maybe 800 miles an hour. It doesn't matter. But here's the center of the circle. So in New York, there's the center of the circle, and this is exaggerated. You need a centripetal force in that direction. The plumb bob, the weight on the bob is towards the center of the Earth. So there's the center of the Earth. Okay, and so the force, the weight of the Earth and the tension that the plumb bob exerts on this mass those two should add up to give you that centripetal force. Okay. So it turns out that the plumb bob, this is kind of hard to draw. Okay, let's see. So let me use another. So I'm just going to draw so here is in New York, here's the object. The force of gravity is in this direction. And the plumb bob will be at an angle like this, such that the force of the plumb bob is in this direction. So these two forces combine to give you that centripetal force. This is mind-blowing. Okay, so the plumb bob is pulling you in that direction. It's not pulling you vertically up. If it pulled you vertically up, these two forces wouldn't combine to give you that centripetal force. So when you're building in New York, you're building it tilted towards the North Pole. So buildings in New York are tilted toward the North Pole. Building in Buenos Aires are tilted towards the South Pole. Only at the equator are the buildings straight up, and Santa Claus's building is straight up at the poles. Okay? In fact, so for non-zero latitudes, Fs is no longer pointing away from the center of the Earth. Okay, so this force is tilted towards the North Pole. It's tilted towards the pole. A plumb bob will always point along this deviated direction. All buildings are built aligned along this deviated direction. For the tallest building, this represents a deviation of a few feet at the top. So the tallest buildings are a few feet away from this vertical line. So the Empire State Building is not like this, it's like that. Actually like that. That's the north in this room. Okay. All right, we'll stop here.